and we're going to go ahead and finish up our last problem on exam 2. So question 4, more quantum mechanics, no problem. So I'm still interested in this kind of quantum phenomenon, but I found a new equation that luckily is a series of a function of sines and cosines. So I have this equation, and there's some frequencies in this equation. I also checked a new theoretical paper, and they found additional frequencies that they reported. So I'm still trying to, again, measure these different frequencies. So let's list out kind of these frequencies that we're working with. So I know that in here, remember, this is always omega, right? So it's sine of omega t. If you know that omega equals 2 pi f. So I know that if omega is equal to that, so I know that one of my frequencies, so I'm going to do my f list, my frequencies list. So I have 587. These are all in hertz. So 587. I also have a frequency at 7, 8. Actually, let's go ahead and do this in Mathematica. So, let me go ahead and cancel this out. So quit the kernel. So I'm going to do my last problem. Yeah, hooray. So I'm going to do my frequency list. So F list. So my first frequency list is 587, then 7, 8, 9, 3, 2 divided by 2. Why divide by 2? Because again, it's 2 pi. I have basically 0.4. I could do that math. And then I finally have 1.5 divided by 2. So, and then also, if we look down below, put a comma there, 1.5 divided by 2, I have 75203. I have pi, so basically 1/2. So, because divided by 2 pi. And then I have 17.36 divided by 2. So, oops, let me go ahead and do this. 1 divided by, 1/2. 17.36 divided by 2. So, let's go ahead and look at these values numerically. It's going to take a little while, blah, 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 et cetera, et cetera, et cetera. And actually, what I'm going to do is also sort these as well. So I'm going to sort these by lowest to highest, and I want to look at these numerically. So these are my lowest frequencies and my highest frequencies. So now I know that in order to sample this signal correctly, I need to make sure that my f sub s, so I need to make sure f sub s is greater than 2 times 75203. So that's my first condition. Then to avoid signal aliasing, looking at all these signals here, so lots of these values, 0.5s. So I probably need to make sure that I have a delta f to hit all those different frequencies, delta f of 0.01, most likely, least common denominator. So those are the parameters that should work. So let's go ahead and see what we have and then figure out, well, first off, if we're unconstrained by technology, what would be our sampling frequency and the number of data points that we would select. So if I'm unconstrained by technology, I would do basically 5 times 75203. Again, that's greater than the value, so this would be my f sub s me. Then I know my delta f me is going to be equal to 0.01, so that's going to be that value. So now I could solve for my delta f me equals f sub s divided by big N, so that's me divided by big N, and that would give me the values that I need to kind of solve for here. So if I just did this, let's just say I just change it to 3. Boom, boom. Again, it doesn't really matter too much, but again, they still meet all kind of the constraints here. So that would be a completely valid way to kind of solve this problem. So that will work because I'll hit all these different frequencies, right? N times, you could kind of, figure out 0.4 divided by delta f me. Actually, if I do this, if I do my f list divided by that, you see these are all, integer values. So 1, 2, 3, 4, 5, 6. There's still the integer values of this up here. If I didn't hit, if these were non-integer values, so if this was 40.6, then I'd have something wrong. I'd get spectral leakage. That's kind of the issue here. I wouldn't be hitting those values. So those will work. And again, we've kind of covered that already in class. Can you explain? Now let's look at the DAX and see if anyone kind of hit those kind of concepts. So let's say so right now I have that my f DAC A, so my sampling frequency of A is equal to 75 megahertz, so 75 times 10 to the 6th, and then it could take the n of A can take up to let's see, 17 million, so 17 times 10 to the 6th. So we got that, and then I have FB, or actually NB. Actually, I'm going to use all these lowercase because that'll make it a little bit nicer. So NB is 5 billion, so 5 times 10 to the 9, and it could sample every microsecond. So if I could sample every microsecond, so 1 divided by 1 times 10 to the 6, so 10 to the minus 6. So actually, my sampling rate is every microsecond. Excuse me, my nose is running. That'll be my delta F. So a million. So my N, actually FSB is equal 1 times 10 to the 6. Because that'll give me a microsecond. So if I sample by that, then I'll get those values. Excellent. And then finally, it could sample every nanosecond. So we know that that's going to be just FSC is going to be equal to 1 times 10 to the 9. Because again, if I want to do my F sub S, 1 divided by 1 times 10 to my delta T every nanosecond, 9 is 9. 9. There we go. And what is our NC? It's going to be 400K, 400 times 10 to the 6th, or to the 3rd, excuse me. There we go. So those are our values. So let's go ahead and kind of put us into the very, very, very like limit. So let's say that we are right on the edge of our Nyquist frequency. So let's do 2, and let's say that we always have to be integer values, so 2 plus 1. And that's my delta. So this is the smallest sampling frequency that we could kind of work with that will still properly sample the signal. So now let's look here. 15046. So let's look at our FSA. So we are over that. So we're good to go on that side. FSB, good to go. FSC. So in terms of signal aliasing, we're fine. We could sample fast enough. Now comes the question of time. So with that delta F, which is this, basically the largest resolution we could have, but still hit all these different values, we need to ask the question, okay, can we reach this number of data points? So let's again look at NA. So this is 1, 2, 3, 4, 5, 6, 7. So 1.7 times 10, so let's just make sure again. So NA can work. So NA will work for this problem. So we're good to go there. What about B? B will also work. So times 10 to 9, this is times 10 to 9. What about NC? NC is the only one that does not work. So NA works, NB works, but NC does not work. So again, so they all will be fine in terms of signal aliasing. They have the capability to just sample fast enough, but spectral leakage is the killer. So it kills off C. So A and B completely will work fine. So we had a technology, we could do it. And again, hopefully this is helpful. Please come to the review session ask some additional questions, and then good luck on your exam too. You'll do great just like you did on exam 1. So I'll see you all next time. Thanks.